Okay, welcome everybody. We are going to cover section 4.6. So in our course, let me go to modules. Hang on, this thing's jumping all around. And we are in week 10. And here is 4.6 form. It's a form for 4.6. I don't have a PowerPoint for 4.6. It's just a form. If I was you guys, I would print one of these out and when you're doing the homework, maybe break this out and take a look at it. That's because this is what I'm going to follow today. Now, normally for me, it takes 1 or 2 boards to do this problem. So I'm going to try to abbreviate it in some way by not taking the derivatives. And I'm just going to write down what the derivatives, what the book says, because just the derivatives themselves were going to take me a whole board to do. So I am on page. By the way, is the summary of curve sketching form up right now? Can you guys see that? I wasn't sure what you guys could see. Can anybody see the summary of curve sketching form that I have in front of me? Yes?
Yes.
Okay, good. All right, so in the book, section 4.6, I'm going to do example 1 in the book. So you can actually go back to example 1. The thing about example 1, and any example in here, they don't tell you how to do the derivative. You just have to know. I mean, here is the function that we're going to deal with. X squared minus 9. Hang on, I'm trying to mess with this a little bit better. Divided by x squared minus 4. And we're going to try to fill in all these blanks. So here's our function. Now, once again, you have to use the quotient rule to take this first derivative. I'm not going to go ahead and do that. I really do recommend that you do the derivative and see if you get the same thing that the book has. This is the first derivative for the book. So that's the first derivative. Oh, I feel like I'm missing something. Oh, no, we'll just keep on going. And then the second derivative looks like this. Once again, I mean, it would take us an hour on this system to actually take these derivatives. You'll just, once again, use the product rule. And on the bottom, you know, F is the top, G is the bottom. And you'd have to use the quotient rule and the chain rule for that bottom part, G. The second derivative should look like this. Negative 20. 3x squared plus 4, all divided by x squared minus 4 to the third. Now, if you look, you're supposed to square the bottom. It should be x squared minus 4 to the fourth. But what happens is there's a factor on top that's x squared minus 4, and it cancels out with 1 on the bottom. So this is the second derivative. Okay, from here, we're going to use everything we've learned from section 4.1 to 4.5 and a lot of algebra. There was a lot of algebra to get to the second derivative, by the way. So first, we're going to find the x-intercepts here. X-intercepts are are when the top of your function equals 0. And we're talking about the original function, right? When we do the x-intercepts and y-intercepts, the top of our function equals 0. So when we look at that, just the top, well, you can write the whole function down. I just want to, a lot of people are a little confused about that. Now, this is the function. When you make the function equal to 0, you find when y equals 0, there's y, you can find the x-intercepts. If I multiply both sides by x squared minus 4, x squared minus 4, that all cancels. That turns to 0 because you're multiplying it by 0. So then I'm left with 2x squared minus 9 equals 0. Divide by 2, and I'm left with x squared minus 9 equals 0. 0 divided by 2 is still 0. Take the 9 to the other side and square root both sides. X equals plus or minus 3. Those are my x-intercepts, okay? So my x-intercepts are 3, 0, and negative 3, 0. So we want to fill in all of these blanks. And I don't have my drink with me. I'm going to go get it. I don't really thought I had it sitting here somewhere. I'll get it. Give me a second. I'm going to erase the x-intercept. Well, I'll go get it and then I'll erase it. Be right back. Just a second. Where's my cup? All right, so we have the x-intercepts. Let me erase this now, this part, because I need a lot of room. We have to find the y-intercepts. Here's the original problem again. Now we're going to look at the y-intercepts. Here's the original problem. And the y-intercept is when x equals 0. So all the x's we change to 0. And I end up with 2 times negative 9 is negative 18. 0 squared is 0 minus 4 is negative 4. So the y-intercept, if you reduce it, is negative 9 over 2, about negative 4.5. The y-intercept, x is 0, y is negative 9 over 2. Wait a minute. Anybody see what I did wrong? 0 minus 4 is a negative 4. So it should be a positive 9 over 2. There we go. So we're moving on to the next, finding the vertical asymptotes. See, what we want to do is fill in all of this stuff that we have here and then draw the graph. Using all this information, we want to be able to draw the graph. Vertical asymptotes are when the bottom of the fraction, what makes a bottom of the fraction, what makes a bottom of the original fraction equal to 0. So we're doing vertical. Let me change it back to black. Asymptotes, and the bottom of the fraction, bottom of the rational equation is x squared minus 4. And there are 2 numbers that make it equal to 0. X equals 2 and x equals negative 2. Those are the vertical asymptotes. X equals negative 2 and x equals positive 2. Horizontal asymptotes. Can somebody tell me what the horizontal asymptote is? Anybody know? Hope somebody's awake here, or you guys just turn your computers on and go to sleep. You're watching TV, playing your Xbox. Anybody know what the horizontal asymptote is here? Oh, I see somebody typing something in the chat box. I caught Ian. The horizontal, remember we talked about this last time. The horizontal asymptote, if the powers of the original equation are the same, then the horizontal asymptote is the numbers in front of the powers. And horizontal asymptote always starts with y equals, the answer is y equals 2 over 1, or y equals 2. That's the horizontal asymptote. All right. Next, we're going to learn something from one of the sections we actually covered now. Critical numbers. Critical numbers. How do you find the critical number? Now, there's two things I really want to focus on here. Critical number and inflection point. There's a difference between these two. Critical number is when the first derivative equals 0. Inflection points are when the second derivative equals 0. So it's really important that you understand the difference between these two. Critical number is when the slope equals 0, right? It's the valley or the peak. A critical number is the highest point or lowest point, a relative minimum or a relative maximum, a valley or a peak. All these words are the same thing we've used over and over again. An inflection point is when the second derivative equals 0. Inflection points are where the concavity changes from concave up to concave down. So critical numbers are where the slope equals 0, right? Relative minimums or relative maximums. Inflection points are where concavity changes from concave up to concave down. All right, so I'm going to erase that now and then actually find out the answers. So to find the critical numbers, let's take the first derivative, which is right here, and set it equal to 0. 20x over x squared minus 4 squared, and set it equal to 0. Do you see if you multiply both sides by the bottom, x squared minus 4 squared, x squared minus 4 squared, I'm just left with 20x equals 0. 0 times this is still 0. Divide by 20 and x equals 0. That's a critical number. That's where we have a relative minimum or a relative maximum, a valley or a peak. Okay, so we did find one critical number. One number will make the first derivative equal to 0. And that one number is x equals 0. Now we want to find the inflection point where the second derivative equals 0. Here's the second derivative. Negative 23x squared plus 4 over x squared minus 4 to the third equals 0. If I multiply both sides by the bottom, it goes away. Divide both sides by negative 20. 0 divided by negative 20 is still 0. Get the 4 to the other side. Negative 4 by subtracting 4. And then divide by 3. X squared equals negative 4/3 square root both sides. You cannot square root a negative number. So possible inflection points, there are none. There's no place where concavity changes. In other words, the graph doesn't go concave down to concave up. It stays at that one for each section. So there's no place that concavity changes. There is no second derivative that equals 0. That's not too bad. The domain for this function, by the way, the domain, remember, domain is, look at the bottom here. You can look at the asymptotes. X cannot equal 2 or -2. Those are those vertical asymptotes, right? So the domain is -infinity to -2. And then from 2, -2 to 2. And then from 2 to infinity. In other words, x cannot equal -2 or 2. You could just write, I mean, this is one way of writing the domain. This is called the interval notation. Or you can just write all real numbers except x cannot equal 2 or -2. So either way is fine writing the domain. Testing for symmetry. This is algebra. I see what makes this, I think, easy for symmetry is if you look at the original function, it has an x squared on top and an x squared on bottom. Remember how to test for symmetry? If you're symmetrical with the y-axis, if you replace x with -x and you get the same function, then it's symmetrical with the y-axis. For the x-axis, symmetrical with the x-axis, if you replace x with -x and you get the opposite function, then it's symmetrical. You know, you get the same function with a negative sign in front of it, then it's symmetrical with the x-axis. If you look here, if you replace these x's with -x, then -x squared is still x. Nothing changes. You see, if you replace x with -x and you end up with your same function, then it's symmetrical with the y-axis. So if I put a negative in here, I wouldn't get a negative function in front of that. You couldn't factor out a negative because it didn't change these signs. So this function is only symmetrical with the y-axis. All right. Looks like we've just about filled out everything we needed to. So what I'm going to do now is scroll down, and I think what's going to happen is I have to erase all this stuff. Let me do the test intervals. So now we have to put it in our table, our test intervals. What did we use? If you remember what we used to find the test intervals, I'm going to erase some of this here. To find test intervals, I'm going to write it down in blue. We used To find the test intervals, we use critical numbers. We use critical and asymptotes. We use critical numbers and asymptotes. Our critical number was 0. And our asymptotes, breaks in the graph, right? Our breaks in the graph were right here. Oh, there we go. So those are where our breaks are in the test intervals. That's our breaks in the test interval. So our test interval should go from negative infinity to the first one of these, which is -2. Then we're going to go from -2 to 0 because the next number that I see is critical is 0. Then I'm going to go from 0 to 2. And then finally, I'm going to go from 2 to infinity. So this is our test interval, negative infinity to -2, -2 to 0, 0 to 2, 2 to infinity. We use our vertical asymptotes and our critical numbers to do those test intervals. All right, so now that we have that, I'm going to scroll up, and we're going to lose all this information. Luckily, it's being recorded. Hopefully. Is it being recorded? Let me see. I think we're being recorded. Yeah, we're being recorded. So let me clear this and scroll this up. And we're going to fill in this box. See what we need to fill in that box, and then we need to graph it. I think I'm just going to break it out on the calculator to show you the graph. So we're going to fill in the box. So this is the way we do this one, the graphing one, is a little different. Alan, what did you have a question about 2 for? Did you have a question about 2?
2 was from earlier. He was giving the answer.
Oh, sorry. I just saw the chat box. All right, so we're going to place our test interval in here. Our first test interval was from negative infinity to -2. Now, we also have to put these important points in our graph. And the important point is -2, x equals -2. We have to add these in here and find out what's happening at these particular points. Our second interval was from -2 to 0, so our next important point was 0. Our next interval was from 0 to 2, and our next important point then would be x equals 2. And finally, we went from 2 to infinity. Okay, so there's our test interval that we had to do. And in between the intervals, put those important points that we use to find the intervals, because we want to explain those points. So in this first interval, the only thing I want to know, actually, let's do this in all these intervals right now. We're going to do the first derivative in all of the intervals. We're going to do the first derivative for all the intervals. Somebody, oh, where's the original problem? I'm going to write the original problem down here. Let me, I can't raise it anymore, but I'm going to write the original problem here. Oh, I have to write the, sorry. I have to write the first derivative because we're going to do the first derivative right now. Our first derivative was 20x over x squared minus 4 squared. Okay, so we're going to do test points and find out what the slope is. Was the slope positive or negative at each one of these? Remember, that's what we did. I think it was in 4.2 or something, where we found the intervals. Then we did test points in each interval to find out if the slope was positive or negative in that interval. So I'm going to pick a point in this interval. And I'm going to write down the point between negative infinity and -2 is -3. So I'm going to use that point, and I'm going to plug -3 in here. 20 divided by -3 is -60. If I plug -3 down on the bottom, I get 9 minus 4 is 5. 5 squared is 25. I get a negative answer. Do you see? So I'm just going to put a negative slope. I get a negative slope. I'm going to do the next one now. I'm going to go right down the intervals. And I'm going to pick another test point between -2 and 0, -1. So I'm going to use that as a test point. I'm going to put TP here, toilet paper, or test point. Plug -1 in here. -1 times 20 is -20. -1 squared is 1. 1 minus 4 is -3. -3 squared is 9. I get a negative answer. I'm going to keep on going. I'm going to go down to the next interval. And I'm going to put 1 in here. 1 is in that interval between 0 and 2. When I put 1 in there, I get 20 on top, and I get 9 on the bottom. I get a positive number. So the slope is positive in this interval. Then I'm going to put a test point in here, 3. 20 times 3 is positive 60. 3 squared, 5 squared is like 25. So I get a positive number, and I get a positive slope in that interval. All right, so we pretty much did all of the intervals with the first derivative. Remember our asymptotes at x equals -2. This was an asymptote. So I'm going to put at -2, you can write asymptote, or you can write it's undefined. Undefined. When you plug -2 into that, if you look at here, if you plug -2 into that original problem, it's an undefined slope. Undefined slopes are vertical lines, right? That's an asymptote. Same way with 2, if you plug 2 in there, it's an undefined slope. First derivative is telling you what kind of slope you have. Undefined slope. It's an undefined slope. And once again, it's an asymptote. But if you look at it, that asymptote has an undefined slope. And finally, at x equals 0, when we plug 0 into this function, at x equals 0, look at the first derivative, and that's not right. Is that the first derivative? I wrote the first derivative down correctly. Oh, yes. If I put 0 into this function right, in the first derivative, I lost my pen. Okay. If I put 0 into this function, 20 times 0 is 0. Put 0 down below, I get 16. I get 0. I get a 0 slope. What does a 0 slope mean?
It's just a straight line then?
It's a horizontal line, yes. See, these are undefined slopes, and this is a 0 slope, which is just a horizontal line, right? And that's where we have a minimum or maximum. Remember, at 0, we figured out that's where we have a minimum or maximum. It's a valley or a peak. Yeah, you see the horizontal line. That's where our slope is 0. All horizontal lines. Our slope is 0. I'm just going to put down our slope is 0. First derivative is 0. All right, so we answered all of those. Wow. Let's go to the second derivative. Let's see if that means anything to us. The second, remember when the second derivative, we put a test point in there. It's going to tell us negative or positive. Let me write down the second derivative. Does anybody remember what the second derivative, what does a negative mean? And what does a positive mean? I think I'm going to have to go back and read that for you. When the second derivative is negative, I'm going to tell you what page that's on here in a second. I think it's in 4.4. 4.4, 235, the second derivative test on page 235, section 4.4. When the second derivative is positive, oh, wait, no. Is that the one? Where is it? Oh, here it is. It's the one on page 232. When the second derivative is positive, you're concave up. So this is, I better write it down. So second derivative, this is the test for concavity. I'm gonna put test concavity. It's on page 232. When the second derivative is positive, it's concave up. When the second derivative is negative, it's concave down. Yep. All right, so that's what we're testing next. I'm going to type in the second derivative. Oh, Lordy. That's why I'm only doing one of these. I only do one in the classroom also. It gets too crazy. And I use the whole board. So where's the rest of it? X squared minus 4 to the third. All right, so we're going to do the test point once again. We're going to use the test point of -3. Maybe I should have wrote the test points on the side. If I put -3 in here, I get a positive times a negative. I get a negative on top. If I put a -3 on the bottom, I get a positive on the bottom. Negative divided by a positive is a negative. All right. So next I'm going to put a test point of -1 in here. Oh, yeah. I might as well write, it says characteristics of a graph. So we're going to do this. Do you see characteristics of the graph? This tells us that in this interval, the slope is negative. It's a decrease. Well, they say decreasing or increasing. It's decreasing function. It's a decreasing function. And a negative slope means concave down. So if I put -1 into this function now, put -1, I end up -1, that's a positive, times a -20, I get a negative. On the bottom, if I put a -1, I end up with -3 to the third, which is a negative. So this becomes positive. So once again, the slope of this interval, -2 to 0, is decreasing. It's negative. And we got a positive, which is concave up. All right, so I'm going to go to the next interval, which is a +1. Put 1 in here, I get positive times a -20, which is a negative. Put 1 down there, I get a negative. Negative divided by negative is a positive. So once again, this was a positive, so it's an increasing function. The slope is positive, so it's increasing, and it's a positive second derivative, so it's concave up. And finally, my test point 3. Put a 3 in there, I get a positive times a negative. I end up with a negative on top. Put a 3 in there, I get 9 minus 4 is 5. 5 to the third is positive. Negative divided by a positive is a negative. This is a positive slope increasing function. And negative means it's concave down.
For the test point -1, you put decreasing, but you put concave up.
Yeah. No. Yes, we're using the test point -1. It's decreasing because the slope is negative. Let me show you once again. I'm going to put.
Will it be concave down since it's decreasing?
Well, let's put -1 in there again. If we put -1 in here, see, first we put -1 in this. This is the second derivative. Let's check it out. If I put -1 in here, this is still positive, and times a -20, that's negative. If I put -1 down here, I get 1 minus 4, which is a -3. -3 to the third power is -27. Do you see? It turns positive. The second derivative is positive. When I put -1 in the second derivative, it's positive. When I put -1 into the first derivative, it's negative. This is the first derivative side. This is the second derivative side. But I see what you mean. Wait. Something doesn't seem right. You're right. Something doesn't. Oh, wait. Let me see. No, negative. I'm looking at the book now. Negative, positive, positive, negative. No, we're okay. Do you see how I got that positive? I think the question you're asking is, how did I get this positive? And you have to put -1 into the second derivative. And I get a negative on top. I get a negative on the bottom. Negative divided by negative is a positive.
Okay, I got you.
Okay. See, I put a -1 in. This is the first derivative. We put this -1 in the first derivative and got a negative answer. That means it's decreasing. When I put a -1 in the second derivative, it said it was positive. That means it's concave up. This was the first derivative side. This is the second derivative side. Okay. What else do we need to know? Oh, there's one more thing I think we need to really look at, and it's at this point right here for the second derivative. I'm going to change my color. It gets a little busy here. I need to put 0 in here. So because it's not a test point, it's 0. So I want to plug 0 into the second derivative. Let's do that now. And then I'm going to show you what we have to do with that. But let's plug 0 into the second. If I put 0 in here, 0 plus 4 is 4. 4 times negative 20 is negative. Put 0 down here, I get negative 4 to the third power. It's negative. Negative divided by negative is a positive. So if I put a point, if I put 0, I get positive. If I put that point 0 in there, it's positive. Now, you have to go back to the last section. Remember the last section, the last video we did 2 types of problems, finding out where it was concave up or concave down. And then we used the second derivative test, or not the last section, 4.4, the next to the last section. So on the first part, on the first part that we did, all of these just tell us if they're concave up or down. If I just put, because those are test points, but if I put a critical number in there, the second derivative, see, for all those we used theorem 4.7, which is on page 232, tells us if it's concave up or down. But then for the particular points, we didn't use intervals anymore. On that last problem on 4.4, we didn't use intervals anymore. We used specific points. We used the critical numbers. And if you plug those in, the second derivative is positive. You have a relative minimum. So this, I'm going to actually write that down on page, I want you to look at these, 235. So you need to look at page 232, the test for concavity rule. I mean, it's really important that you look at both of these and really understand them. Test for concavity. And then page 235 is the second derivative test. Even though they're both second derivative tests, this one's just called the second derivative test. This determines whether it's a minimum or maximum. Second derivative test determines if that point is a minimum or maximum. And a positive, we got a positive for that number. A positive is a relative minimum. If the second derivative is greater than 0, if the second derivative is positive, we have a relative minimum at that point. We have a relative minimum at that point. Okay, so make sure you go back to the book, 232 and 235, and read those. They were in the PowerPoints. But I want you to look at them in the book, and I think that might help just a little bit. Now I got to find out where I'm at. Oh, here I am. And we're done. We pretty much wrote down everything we needed to. And what you're supposed to do now when you have this is graph it. Oh, Lord. I'm going to put the original function in my graphing calculator. First, I have to find my graphing calculator. Give me a second. There it is. That's not my graphing calculator. That's an old one. Come on now. What do I do with my graphing calculator? It's underneath all my papers. So I'm going to go to y equals and type in the original function. Don't forget, I'm going to go ahead and erase this and type in the original function that I'm going to type in my graphing calculator. The original function was 2 parentheses x squared minus 9, all divided by x squared minus 4. So let me put that in my calculator. Divided by x squared minus 4. I've got to put those in parentheses. And hit a graph, make sure my window is correct. I'm putting my window at negative 10, 10, and negative 10, 10. All right. Hang on. Get this back. There we go. Give me a second. Can you guys make my... Are you guys able to make my screen bigger? There we go. Are you oh, I'm going to change my video if I can find it. Are you guys able to see my calculator now? Is it big enough for you guys to see it? Can you make it bigger or something?
It works.
Okay. So if we look at everything we just wrote down, so we wrote down between negative infinity and negative 2, we have a decreasing function. Do you see from negative infinity to negative 2, this is negative 2, the asymptote, this function is decreasing. Do you see how it's going down? Then we wrote down from negative 2 to 0, it's also a decreasing function. From negative 2 to, we're talking x values from negative 2 to 2. From negative 2 to 0. Here's negative 2, here's 0. The function is decreasing there also from negative 2 to 0. Then we wrote down from 0 to 2, the function was increasing. From 0 to 2, the function is increasing. The slope is positive here. And then finally, from 2 to infinity, from here's 2 and here's infinity, from 2 to infinity, the graph, the slope is increasing. So that was the first derivative that we did, finding the test points, and it shows you that slope is decreasing, it's decreasing here, it's increasing here, and it's increasing here. We have the asymptotes at negative 2 and positive 2. We also have at x equals 0, we have a relative minimum. Do you see at x equals 0, here's x equals 0, that's where that slope was 0. We have a relative minimum. It's a valley. That's a relative minimum. What else did we have? Oh, concavity. Here, this is concave down. From here to here, this is concave down. From here to here, From here to here, it's concave up. And from here to here, do you see it's concave down? and you should be able to draw all that. There is a horizontal asymptote, we said, at x equals 2 also. We said there was a horizontal asymptote at x equals 2, or I mean, sorry, at y equals 2 when you go across here. And this point right here, that relative minimum was 0, 9 over 2. Remember, 4.5. That point there on the y-axis is at 4.5. That's the y-intercept. That's the only place the graph crosses the y-axis at 9 over 2, 4.5. And that's from all this information you have here, you should be able to graph this. You should be able to. And if we were in class, I would actually make you do that. Give me a second. There was something. Oh, down here. I'm going to clear all this. If we were actually in class, I'd make you actually draw that. You have to actually, go through that whole process and do the test points and draw the actual graph. So you won't have to do this on the test, but when you're doing this homework, look at it and understand what each part is, because each part is separate. We just did maybe 10 test questions today. 10 test questions, finding whether the first derivative, whether the slope is, whether it's an increasing function or a decreasing function. The second derivative, whether it's concave up or concave down. The second derivative test, when you use a particular point, whether at that point we have a relative minimum or a relative maximum. So all of these are test questions. This is just all these test questions grouped into one. And that's all I had today. Any questions? That took about an hour. Normally it takes the full hour, and then I have you guys do one in class. And
This is all recorded, right, Professor? And we can watch it again?
It's recorded. I'll post a recording probably about 2 hours. I'll put it on the website in the module.
Okay, and all the
Professor?
all the classes are recorded?
Yes.
Professor, I have a question.
Yes.
I using the all edition book. So what is the name of this topic today?
This is 4.6, a summary of curve sketching.
Okay, summary, because my book is old version.
Summary of curve sketching, and I just did example 1. There are like 4 or 5 examples in this section, but I just did one example, example 1.
Okay, so summary.
Summary of curve sketching, yes.
Okay.
You can actually look at the online book. You have an online book, so you can actually look at that online book.
Okay.
In the online book, it's section 4.6.
Okay.
Okay, so you can actually go to the online book in the homework section, go to section 4.6, it's example 1.
Okay.
Okay.
Thank you.
Any other questions?
No,
wait, let me check, make sure I have all the roll here. Nisa, did you show up? All right, did everybody leave already? No, I don't. Did Nisa show up? I don't. Oh, she's here. Enrique, are you here? Enrico, yes. Nicholas, I think I saw you.
Here.
Yes. Crystal and Jeffrey.
Here.
Okay, good. Melvin, yes. Sierra and Jose. Jose's here. Sierra. Nope, one person missing. All right, you guys have a good weekend. Don't blow it off. Make sure you understand this homework. Do the homework, and don't just get through the homework. Once you do the homework, go back and see if you can do the homework without any help. That's what, when you really know you're starting to learn, is when you can start doing these problems without any help. I know sometimes a homework problem is difficult, maybe a little harder sometimes, but go to the examples in the book and look at that. If you're done with the homework, open up the online book and go to those examples and see if you can follow. Like here in this section, they just tell you what the first derivative is. They don't show you how to find it. They assume you know how to use the quotient rule already. Verify that you can get the same thing that they get using the first derivative rule. And then the second derivative, take the derivative of that. Those usually take a long time. I mean, taking the first derivative in the quotient rule and the second derivative in the quotient rule and try to get what they get in the book. There's a lot of algebra involved to get that, what they get in the book. So practice that. And don't just finish the homework, but study, go back into the sections and do that. I'll be here this weekend. If anybody has any questions, feel free to email me or call me if you have any questions. And I will see you Tuesday.
Okay.
Bye, all.
Bye-bye.
Professor, real quick, as far as your availability, if we were to give you a phone call, what would that be?
8 in the morning till 7 at night.
Well, okay. Thank you so much.
If you want to email me and make an appointment, just email me and say, hey, I'm free on Saturday at 10 a.m. Are you free? And I'll say yes, and then I'll turn on the Zoom and we'll meet.
Great. Thank you so much, Professor.
Sure thing. I'm not going anywhere.
You on Canvas to set up an appointment?
Yeah, just email me in Canvas if you want. Just email me in Canvas saying when you're free, and then I can get online with you.
Okay, thank you.
Sure thing. Any other questions? Any other questions? All right, you guys have a good day. I'm gonna hit the road.